In this video, we're going to continue our review of Python inside of Rhino through a series of exercises, first mirroring some early exercises that we performed in earlier videos in both Rhino and Grasshopper, looking at some geometry types as well as the rhinoscript syntax variables and objects, and then we will get into a couple of operations using loops, specifically looking at a couple of examples developing mathematical curves and surfaces by a former professor of mine, Joseph Choma. To get started, just like in the previous Python video, I'm going to double click into our perspective space. For now, I can actually hide this grid as well because we are going to be using the viewport more than we did in the first Python introduction video. So I'm going to type in the command line grid, type H, enter, enter, and we've removed that grid from our view. Just like last time, we're going to use the Python script editor. So we can go up to our tools menu and then go to Python script and then click edit. So as we did before, at the top, I'm going to make a multi-line comment which tells us a bit of information either about ourselves or the kind of context in which this script is created, or just the topic of this script. So I'm going to start that with triple quotes. And then in between those triple quotes, we can write a bit of information here. So I'm going to say, Introduction to Python exercise, loops, and mathematical surfaces. So we're going to be using loops to actually be able to construct mathematically these surfaces. So that's why it's a combined exercise, but we have to kind of go through the early steps and really understand how Python can interact with Rhino geometry before we get back into more complex data structures like loops, and then kind of connect them together in order to approach these mathematical surfaces. So I'll just leave it simple like that for now. I suppose we actually could just put our author name as well if we wish. What we need to do to get started, if we know that we're going to interface with Rhino geometry, is import a preset library or pre-built library, which we did go over at the very start of the introduction to Python video, but we may not have known that that's the specific library or how we might interact with it. So what that library is this rhinoscriptsyntax library. And as I mentioned in the previous video, if I click this drop down arrow here, we can see all of the different objects present inside of this library. And if we click on something like curve and the drop down to it, we can see that there are certain commands or functions like add arc or add curve or add line, add polyline, add NURBS curve. These are already looking pretty similar to what we've used as components in Grasshopper or used as commands inside of Rhino. So they're going to be almost identical to those commands. It's a very similar overall structure to our command line interface in Rhino or the component library inside of Grasshopper. So it's just a slightly different way of interacting with basically the same things. So if we want access to that library, what we need is to actually bring that library into our script. So we need to add a reference to that library. So we do this with what are called import statements. So I'm going to just write a note here. Import all libraries needed for this script. If we want to use Rhino geometry, then we can go ahead and just import using the statement import that rhinoscriptsyntax library. And you can see that as soon as we type import and hit space, it actually already autofills all of these different options for libraries that we can import inside of the Rhino environment. So we're going to go ahead and just select rhinoscriptsyntax. And when we import these libraries, rather than typing this entire name out every single time we refer to it, we can actually store it in a variable just kind of nicknamed something else to refer to this library. So a common one is to say import rhinoscriptsyntax as rs, where rs is just a nickname that we set. So we're saying import this and call it rs. So now every time we refer to the letters rs, we can refer to or call things present in that rhinoscriptsyntax library. So now, just like in our introduction to Rhino and introduction to Grasshopper videos, what we're going to go through is a series of different steps constructing geometry inside of our Python script editor and see how that kind of plays out inside of the Rhino environment. So in order to do that, we need to first call this library by typing rs. And to access any of these things that we see in this drop-down menu to the left, we need to add a period. So this period is going to give us access to everything present in that rhinoscriptsyntax list. Now it's already giving us from A to Z a list of certain functions or commands that we can use. What I want to do to start out is use a command called add point. And if we open up our console or slide up or expand our console here a little bit, we can see a little bit easier the add point function and some parameters, both that it takes in, that it outputs, and its description. So we see here that we can call this add point function, and just like when we defined functions for custom functions we made, we see that this is called add point. Inside of the parentheses as inputs are a point parameter. We have a definition for this, or a description, saying it adds a point object to the document, meaning it actually places a point, not just a kind of reference to a point like in Grasshopper, but it places a real point in our Rhino document. And then we can see some extra information below that, which is parameters, and that just tells us what it intakes. So the parameters it takes in are a point, and that's going to be defined by a point 3D or a list X, Y, and Z. So this is very similar again to Rhino or Grasshopper. A point is defined by X, Y, and Z coordinates. Now it's going to return what's called a GUID, which is just a name referencing that point. So we don't exactly have to know right now what that GUID is, but it's best to just think of it like a nickname that Rhino gives to this point. It's kind of like a variable name that Rhino has automatically given to this point that we've created to kind of parse or organize the document in the Rhino environment. So it outputs that point, and then we also see an example here of how we can use this. So it's telling us here in this example that in order to use this add point, we need to first import rhinoscriptsyntax as rs, which we've done on line 8. Then we can say rs.addPoint, and then in parentheses, we give a list of X, Y, and Z values, which in this case is a list here, or a tuple of 1, 2, 3. So our X is 1, our Y is 2, and our Z is 3. It also gives additional things that we might be interested in using, so related functions to this current function. This setup here at the bottom is going to be the same pretty much every single, not the same content, but the same kind of structure every time we use a function from, in particular, our rhinoscriptsyntax library. So this is our best tool. This and this side menu to the left here are our best tools for really understanding and getting a grasp of Python and these libraries that currently are unfamiliar to us. So we know it takes in that 1, 2, and 3 are X, Y, and Z data inside of the parentheses, and we need a parentheses around that data as well. So like in anything in programming, we need to make sure that we open and close. And then inside of here, we can just make a point at 0, 0, 0. Now, if I click play to debug, we can actually see that a point has been made and added to our document. If I move our Python script editor just over slightly and then click details with that point selected, we can see that point is exactly at 0, 0, 0. So we have a valid point made in our document. And actually that GUID that Python said was going to be returned is written right here as this ID, which Rhino uses to refer to this object. So that's what's called the GUID, which is just a set of characters which identify this particular point. Now if I hit close and we go back to our rhinoscript editor, what we're going to do, like in previous videos with Rhino and Grasshopper, is not just make a point, but we're going to draw out 2 points and now make a line, because a line is defined by 2 points. So we can delete that from our file, and we can go ahead and hit enter, copy this line, paste it again, and now if we just change these values, let's say 10, 10, 10, we now have a new point that will be added. So we'll add 1 at 0, 0, 0, and 1 at 10, 10, 10. So when I hit play, we have 2 points being added to our document, 1 at 10, 10, 10, and 1 at 0, 0, 0. If we want to make a line in this file, I'm going to hit enter twice, and we can go back into the rhinoscriptsyntax library, so rs, hit period, and we need to search for the function that can add a line. So like add point, we're going to type add and then line. We can hit enter and then open the parentheses. As soon as we open the parentheses, we get this description or definition or kind of help function at the bottom in our console. Now we can see what this takes as an input is a start and end point, which makes sense as a line is defined by 2 points. So we can give it a point or a GUID, endpoints of as the endpoints of the line. It then returns a GUID and adds a line to our document. It even gives us some information on, or example on how we can use this. So this is saying get a point from our Rhino document, which we could do. Or what we could do is store those GUID values from our first 2 points, and we could store them into variables and then use those variables to pass into this add line function, and then we can make a line from those 2 points. Otherwise, we have no way of referring to those 2 points that we've made because we haven't actually found a way to kind of store that GUID information. So what we need to do is make a variable point1 equals, and then we can make another one, 0.2 equals. So we have 2 points there. And then we're going to make a line, rs.addLine, from 0.1, comma, to 0.2. Now when we click play, it not only draws those points in space, but it also draws a line connecting them. Just like with the points, once we've created that line, we may want to refer back to the line that we've made. So we may want a variable line, and after declaring that, we need to set that equal to some data to be stored in the container. So we can set it equal to the constructed line or the GUID of that line in our document. So we now have 2 points being added to the scene, passed into an add line function, which is then stored in our line variable. Like in previous videos, we want to go from a line now, multiple lines which construct a polyline. In order to do this, we need a list of points. So we could just go ahead and keep adding our points. So we could make a 0.3, and we could say 12, 12, 16 to just change it up slightly. And instead of adding a line, we can comment this line out, and now we can make a polyline called Polyline, and we can set this equal to a polyline function called add polyline. And what this takes is a list of points. So in order to feed information into this, we need an actual list of all of the points that we have created above. So we need a list, which we can call PTS, and we can set this equal to an empty list. Now we need a way of adding each of these points here. So we can just go ahead and place them inside of this list. So PT1, comma, PT2, comma, PT3. Now if we take that list and pass it into our add polyline function and hit play, we're going to draw out a polyline instead of a line in space and add all 3 of those points. If instead of a polyline, we wanted to draw a curve, again, just like in previous videos, we're able to make a curve. So we can set a curve variable, set this equal to the output of a function, and we can set this equal to add curve, open parentheses, and just like a polyline, this takes an input list of points, which we already have called points, so we can feed points in. It also takes an input degree, which by default, it says here, as an input parameter is 3. So that's an optional input, but if we wanted to just specify that, we can just give a 3 input to ensure that that degree of the curve is 3. If we wanted to change that to 2, we could change that to 2 as well. Now if we click play, that's going to make a degree 3 curve based on those points. Instead of just setting or declaring each one of these points individually, I'm going to go ahead and comment these out, and we can go ahead and comment out our list of points and our curve as well. And what we want to do now is actually construct an array of points from 0, incrementing by 1 along the x-axis 10 times. So if we want to do that, one way we can do that is to construct a loop to add points along the x-axis. So to do this, we know that we need the function addPoint, but we don't right now have the information that we need to put inside that, so I'm going to just hit enter, give us some space. We also know, or at least may have an idea, that we need a loop to be able to do that iteration. So just like we did in Grasshopper, we needed that range in order to create a series of numbers which could add points in an array. Similar to that, we need a loop, so we can say for I in range, and we'll just default this value to 10, since we know we need it 10 times. So this range of 10 should give us a range from 0 to 9 and give us 10 points, or 10 values at least. Okay, so we're now looping through 10 times of something. So if we just want to change the x value of each point that's created, and we want to make 10 total points, then what we want to do is nest this function to make that point inside of our loop. And when we pass in point information here, instead of just using 0, 0, 0, what we want to store instead is the I value here. So maybe instead of I, we can actually call that x. So for x in range 10. Now if I set this x value to x, we can go ahead and print x as well, just to see it inside of our Python script. And if I hit play, what we should see are points being added in an array along the x-axis, which we can see there. And we can see it even goes from left to right, from 0, 1, 2, 3, all the way to 9. So what if we want the movement not just in the x-axis, but we also want it in the y? Well, what we could do is just use this variable that we already have and just plug it directly in as x to our y. Now we can go ahead and hit play, and that gives us a line from 0 all the way out to what should be 9, 9, 0, and 10 points in that line array. If we wanted it to happen in all 3 axes, then all we have to do is add that x value into the z coordinate. And now if we hit play, that's a 3-dimensional line drawn out. And like when we were using the graph mapper, if we were to manipulate any of these inputs, so let's say we wanted, let's make this go back to for I in range for now, and we can say x equals I, and then we can say y equals I as well, and z equals I, and then we can make each of these values x, y, and z. Just to make it kind of easier to read here, that's the same thing as what we just had. Now, if we wanted this, let's say, to be exponential curve in 2 of these axes, one of the things that we could do is say I times I, And if we wanted it in both the Y and Z axis, we could do I times I in both axes and then hit play. And we're now just going to step in the X. So step in the X just 0, 1, 2, 3, all the way to 9. But every time we increment I, we're going to change Y by I times I. So we can go ahead and print our X, Y, and Z every single time we step here, and then hit play. Now we can see that incrementing in both the Y and Z. And if we didn't have that in the Y, what would happen is we would draw just a straight line directly between the kind of midpoint of both of these axes, and our Z would curve up. So if we hit play, we can see that exponential curve as it steps up. And we can see that go from 0, 0, 0, and then 1, 1, 1. And then since we're performing that square, the X and Y are just stepping by 1, but now we step by the square value of whatever our I value is for our Z. So 4, 9, 16, 25, and so on. And if we wanted to actually draw a curve through these points, or for now let's just use a polyline drawn through these points, what we would have to do is find some way to store these point values, to then maybe save them into a list, and then we could call that list to add the polyline. So let's go ahead and copy these two lines, since we know that that's what we want. So I'm going to uncomment both the points list and the polyline. So the polyline we want after we've already iterated through all of these points. So I'm going to delete those points, and we can go ahead and just move this polyline by cutting and then pasting. And we're going to just paste it somewhere after our for I in range loop. Right now, we're still just reading these 3 points that we've actually commented out, so they don't exist. So we have nothing in this list. So we just have an empty set of points. We're also not actually storing these points that we're creating inside of our loop in any variable. One thing you might think we could do is maybe open up points and set that equal to our points. But this would override every single time and only store one individual point. And we can even print this just to check, and I'm going to comment out this polyline. So if I hit play here, it's going to loop through, and then all we have in our list of points at the very end is just 1 point, which is the last point that we've stored at the very end. So instead, what we want to do is actually add to this list. If you remember from previous videos, when we had a list, we could type the list name, then period, and it's not auto-filling, but we can use the word append, open parentheses, to add items to our list. So now every single time we create a point, we're going to add those points and infill that into our list. So we're depositing it in the empty box from our list. And I'm going to actually print our points within that loop so that we print every single time we add a point to our list. So if I hit play now, we see that we can iterate through with x equal to 0, 0, 0, and then it adds that point to our list. We then have 1 point in the first step, 2 points in the second, 3 in the third, and so on. And every time we loop through, we add a point until we eventually have all 10 points in that list. So if I back this out and then we run this again, we can see that that list has 10 points contained inside of it. And if we wanted to make sure that it was 10, then what we could do is just print the length of this list, ensuring that we get a length of 10, which we can see there. So we do have a length of 10. Now that we know our list is full and that we have a length of 10, we can go ahead and remove that print statement, or maybe just comment it out so that it's still in our file, and then uncomment our polyline and hit play. And that's going to construct our polyline, or draw our polyline all the way through that list of points. Similar to this polyline, we could also make a curve by using add curve and then feeding in those points. So I'm going to delete everything in our Rhino file, click click play to run it again. And we now have one open curve drawn through those points. And you can see that since it's the NURBS curve, it is slightly off that point set. Now, this is the basic structure that we're going to need for developing these mathematical surfaces. Already, we're performing mathematical operations to define or to basically draw out functions inside of Rhino by setting these equal to increments, whether that's linear, so 0, 1, 2, 3 to 9 for both the x and the y, or in the z using exponential. We could also just add a factor here to increase the slope in this one axis. So instead of y equals I, we could say y equals 2i, or 2 times I. Now if we hit play, we can see that that's stepping twice as much in y. And if we wanted to exaggerate that, we could say times 20 times I. And we can see that that's stepping significantly more. And we can also see that in the printouts of those x, y, and z values. Another way to define this would be to actually use mathematical equations instead of just constructing them here from the loop. So I'm going to comment these out. And then just below, I'm going to add a comment to ourselves and say, add curve with math. This will just be a simple one, but we want basically that same structure. So we want an empty list saved as points. We want a range, or a loop rather. So we can just use, for I in range, 10. We want some x, y, and z variables, and we want to make points and then use those x, y, and z variables to actually do the point construction, and then we can add each one of those to our points list. So what if we want here in our range from 0 to 9 for x to be defined by the sign of whatever value we are getting? Then what we need to do is import another library, and this is going to be the math library. So we can type import and then math, and this gives us access to mathematical functions. Now if we say x equals math dot, this gives us access to all of those mathematical functions. We can then just type sin for sign, open parentheses, and then feed in I. Then we can just say y is 0 and z is 0. Now if we click play, we can see that those x values are ranging 1 to -1 along the x-axis. So that is the amplitude of that sine curve, and we're seeing that it's periodically ranging across the x-axis from 1 to -1 and back. Now the reason why this might look strange is because we're drawing it on a line, and that's because our y and z values are 0. Well, if we just set our y value to I, delete these points, and hit play, this should look a lot more familiar, which is the structure of a sine curve drawn out across the y-axis. If we wanted to do this instead drawn out across the x-axis, all we need is to increment our x value by I, so x equals I, and our y is what's controlled by our sine function. So now when we click play, we can see that drawn out across our x-axis. If we wanted twice the amplitude here, what we could do is add a multiplication factor of 2 times whatever the output is. Now this is going to give us an amplitude as an output of 2 times that sine amplitude. So we're now ranging from 2 to -2 on the y. If we wanted the frequency to change, we would need some manipulation to what's inside of the sine function. So I here, and we could say 2 times I inside of that sine function. And now we can see that that changes from a period of, looks like 2 or 3, I guess it's 2. It's a bit hard to tell with this few number of points drawn out. But then in that second set, it looks like we have a period of 1. So if I click play here again, I think we've actually doubled that frequency. So it looks like maybe it's a period of like 4, and the original one is a period of 2, I suppose. If instead we wanted to decrease the frequency, we could hit play, and now we see it decreasing, which is a period of what looks like about 1.5, going from the x-intercept, coming back to the x-intercept, and then all the way down to -2. If we wanted more of that drawn out, what we could do is increase our loop. So for I in range 100, and now we can hit play. That's now going to make 100 points running the sine function with an amplitude of 2 and half the frequency of a typical sine function. If we wanted to double that frequency, all we would need to do is delete those points and again multiply by 2 instead of dividing by 2. And I think we just have far too few points to be able to really see what is happening there. So if we take a look at what this sine function is actually doing for a moment, so by typing math sine and then opening parentheses, we can see that this sine value takes an input of a float, but right now we're giving an input of integers. Now, what this sine function actually wants is to read in radians inside of it. So it's saying here float, but it wants to actually calculate using radians in order to properly read the I value inside of that function. If we want to translate this I value into radians, what we need to do is multiply by pi and then divide by 180. In order to do that, we need additional math functions. So inside of this math sine function, we're going to add math.pi. So we need first I multiplied by pi, and then we need it divided by 180. We can range from 100 to 180. Now if I delete all of these points, we can see that slowly stepping across there. And if we want it a little bit tighter, instead of ranging x from 0 all the way to 180, what we can do is we can have it in a period of just 1 by dividing by 180. So now if I delete that, it's going to be 180th smaller than what we just had. So if I hit play, we now have that sine function just drawn out from 0 to 1 with 2 times the amplitude as well. If we want to draw a polyline through this, what we can do is just take those points that we're already appending to, and like previously, we can add a polyline and set this equal to rs.add polyline and our list of points. So if I delete these, I can hit play again, and it will draw those points into our Rhino document, and then at the very end, it's going to draw our polyline through those points. So in this case, we don't necessarily need the points drawn, but up until this point, every time we add a point, we add a point literally to the document. So what we might want instead of this add point is to actually use a different function. So I'm going to write the same structure here, but this time we're going to use a function called rs.createPoint. And this create point keeps a point definition, but it doesn't actually add it to the document. Meaning we can use that point reference to draw the polyline, but we're not actually adding those points in our document. So it's going to be exactly the same besides the fact that it doesn't add that point to our document. Now if I hit play, we can see that polyline drawn out from 0 to 1 with an amplitude of 2. And if I remove that amplitude of 2 and delete our polyline and hit play, we can see that drawn out again. And if we extend it to the full domain of 0 to 360, oops, not 380, but 360 degrees. And actually we want 361 from 0 all the way to 360, back to 0. And we hit play. We now have that very typical sine function drawn out. We could do this not just in the y, but we could also do this for the z as well. And now instead of it being flat on the xy plane, when I hit play, it's going to draw that kind of diagonally in both the y and the z. To change the period of one versus the other, what we could do is change this I value. So instead of having it exactly the same for y and z, we could use an addition function, and we could add 180 to that I and then convert it into radians. So now when we hit play, we actually have the inverse happening in the y and the z. Also, instead of addition, we could multiply this by 2, and this will change the frequency of the z. So now we have the z with a different frequency than the function coordinating with the y. We could also divide this whole thing by 2, and it's now going to be half the height in the z as it is in the y. And again, we can do this in each of these axes, defining surfaces or curves entirely with mathematics. To show the kind of extent of this, I'm going to introduce some work by my former professor, Joseph Choma. So what we can do is just take all of these lines here, and we can comment them out, and we'll rebuild very similar structure there after we take a look at some of his work. Joseph has actually written a book called Morphing, A Guide to Mathematical Transformations for Architects and Designers, which is an incredible text that I highly recommend you purchasing. It should still be available on Amazon or wherever you can get access to it. But it's actually a catalog of all of the mathematical transformations that he developed and is referencing from other mathematicians and designers, and their translations by just performing mathematical transformations, so just changes in the math. And he's able to get an incredible range of form being driven purely through mathematics. So even this image here is just driven by math-based curves, and that's it. In the book, he actually gives us the kind of recipes for these. So you can see in this reference by Xiaojie Chen, referencing Joseph Choma's work, he's constructed this kind of morphing tool referencing Joseph Choma's functions, which he actually gives you inside of that book. So he gives you the exact image of what it creates, its functions, and how you can translate it. So he shows you translations in the domain, as are shown here in this midsection. So that's the actual domain of translations, and then how you can actually set the X, Y, and Z values there. And you can see that we're actually using, in this case, a U and a V value. So we're actually using two different values, and that's what allows you to create a kind of surface-like geometry, which had a U and a V, or has a U and a V set of curves. We can go back into Python now and take a look at how to structure this in Python code. So it may already be clear to you that this translation that we have here from lines 51 to 62 is of a similar type, or of a similar structure as those equations in Joseph Choma's book. The one difference being that in Joseph's book, we have what's called a parameterized surface. So even though many of the illustrations there are not showing a surface at all, but they're showing a sequence of curves, or a set of curves, those curves are occurring in not just X, Y, and Z, meaning the curves themselves are not just drawn in X, Y, and Z coordinate values, or drawn across points containing X, Y, and Z coordinate values, but there's also rows of individual curves that are compounding to make groups or sets. So essentially what this means is that we have not just x, y, and z as variables, but we also have, kind of like we have here, a value like I. So I here is incrementing just based on the period of the math functions, so the sine function in this case. If we wanted to not just create one set of curves, but instead we wanted to create a surface structure, what we need is not just I, or we could think of that as maybe U, we also need a V direction, or a kind of V axis of the surface. There's a really fantastic discussion about this on this website, mathinsight.org, and this page in particular is titled Parametrized Surface Introduction. And this discusses a little bit of how we can go from something that's called a parameterized curve, where we can see here we have x, y, and z values, and that curve being drawn out in space. And here our t value, or rather I guess I should say our z value, is just equivalent to that t value. So as we drag this curve parameter up, we can see that that curve is moving through space and slowly incrementing in the z, where z equals t. Now, this function that we're mapping here, or this curve that we're mapping based on the functions, also have x value equal to cosine of t and sine value equal, or rather y value equal to sine of t. So that's just to make one curve. Now if we scroll down a bit, we can see here syntax that translates this one curve into a set of curves arrayed along a different axis. So if we say t there, we might think of that singular dimension as a u dimension, or let's say a row in a surface. Okay, if that's a row in a surface, then how would we structure columns? Well, we just need to input a different dimension into those mathematical functions. So we can see a version of that here where we have a kind of domain in both the u and the v set. So we're looping through in the u and the v separately to make rows and columns. We're feeding in both of those values that we're getting, just like we did with one singular dimension, mapping a parameterized curve. This time we're mapping in these two dimensions, creating rows of curves that then can be used to define a surface. So we're using u here, so u times cosine of v is x, and then u times sine of v is going to be the y, and our v value is just our z. So we can see here that for the first step in the u, we would have a value of 0, and we would then increment in the y. So if I can get this viewport clear enough, we can try and look at this. It's a bit hard to navigate. Not the best controls here. Okay, it's looking like it's not going to happen. But with a value of 0 being fed in, our x value is incrementing from 0 all the way to 1. And we can test that with these u and v sliders as well. So with u equal to 0 and v equal to 0, we have a point at 0, 0, 0. Now as we increase our u value, stepping all the way through to 1, we get our x value there at 1 times the cosine of 0, which should be 1. Now as we step through our v, we're taking that starting point at a u value of 1, and we're tracing the curve just drawn relative to that u value, meaning we'll follow one particular curve or one kind of strip of this surface along the v axis. So if I drag this out, we can see that that just follows that outer edge. And if I step a little bit in and then we drag this out as well, we're still following that same parametrized helicoid, but just in a different kind of strip or row, however you'd like to think about it. But the idea is that we're following one particular u or v axis. So I'm going to go ahead and minimize this, and again we can jump back into Python and try and translate this once more into Python code. So here we were just using one single for loop. That's because we were just using one single value iterating through with our map function. So if we wanted to iterate through both a u-axis and a v-axis plugged into our mathematical functions, what we would need is what's called a nested loop. So I'm going to make a comment here, nested loop for u, comma, v. And what that's going to look like is an initial loop for u in range, and we can just start with range 361, knowing that we'll just loop from 0 to 361, so including 360 at the end, so 0 to 360, a full rotation, and then hit enter. And if we just left this as one singular loop, we'd get exactly what we did before, which is one function or one curve drawn, and we wouldn't have those additional rows. So if we want rows, what we want to do is nest this loop that we have drawn above inside of this loop that we're drawing now. If we open up this browser page again, what this is basically saying is let's step in to one iteration of u. So let's just step one in, and then let's loop through all of the points in this curve. Now we're going to go back to 0 on the v, step in a little bit more on the u, and loop through all of these points at that particular u location. So we can do this by looping through the values in u, and for each value in u, underneath of that, we will loop through the v's. So I'm going to go ahead and jump back into Python, and we can just do a print test so that we can really see what's going on. So I'm going to say print u, comma, or actually we'll do a string first, u value, comma, u. And now beneath this, we're going to do our nested loop for v in range. And we'll say 361 as well. Maybe for now, we can just lower these to 10. We don't need to be doing two sets of 361, which is actually a multiplication. So it's 361 times, which will make sense when we go in to print this, which is far too many print statements for us to feasibly go through. So instead, we'll just change those ranges to 10, and now print v value, comma, v. So when I hit play here, what's going to happen is we step into that first loop, we go into that first iteration, so we're going into that first step of that loop, and we should see it print 0, so u value 0. Now we go down to this loop, because it's inside of this loop, right? So it prints 0. Now we should go into this loop, which is telling us within that 0th step in the u, step 10 times in the v. So we'll then see it print 0 through 9 for the v value. We'll then go all the way back up to the top. Once that loop is finished, we'll go back up to the main loop, and it's going to make a value of 1. So u will be a value of 1, and that u value is going to say u value 1, and then we loop through again 10 items in the v. So if I hit play, we should see that 1 value in the u, 10 in the v, 1 in the u, 10 in the v. When I click play, we see that occurring there. So 1 in the u, 0, and then 1 in the v. Now this would be like saying we wanted to map u and v to our x, y, and we could say print u, comma, v. So this would be like nesting those loops and making x and y coordinates. So an array in both axes, so columns and rows of points using these u and v values. If I hit play on this, we see that that's printing out 0, 0, 0, 1, 0, 2, 0, 3, meaning that the u value stays consistent at 0, while the v value increments all the way through from 0 to 9. So as I mentioned, if we wanted to make an array of points, what we could do here is say rs.addPoint, just to visualize this for us, rs.addPoint u comma v, and then we'll just keep that z value at 0. And if I hit play, what we're going to see is points drawn out by placing a point at 0, 0, 0. And then since that u value stays at 0 for the entire first row, but our v increments from 0 to 9, what we'll see is points drawn out across the y-axis. Then it will step on the x one time, draw out on the y, step one more, draw out on the y. So if I hit play, we'll see these vertical rows, or vertical columns, I suppose, whatever you want to call them, being drawn out in our Rhino space. So I'll hit play to debug this, and we see those exactly as I said, just drawn out vertically. Now, if I delete that, and instead we switch the u and the v, what's going to happen is it will first step one unit in the y, and then it will draw out all across the x. So we can just flip these, v and then u, and if we hit play, we now get them drawn out just flipped. So the matrix is flipped, and we're drawing out first in the x, then stepping in the y, drawing out in the x, stepping in the y, drawing out in the x. So this is the base structure of how we're going to develop these u and v parameterized surfaces. And in Joseph Choma's book, he actually gives the u and v domains, so the kind of period which we're considering these trigonometric functions for, and those are based on the u and v values, or rather the u and v values sit within those particular domains for the functions that he describes in the text. And then again, if we just take a look back at one of Joseph Choma's examples, we can see that we get this kind of twisted sphere or twisted oblong shape, whatever you want to call it, kind of distorted mathematical surface, using a u and v value set within the domain of 0 pi, so 0 times pi, which is 0, and between that and 2 pi in the u, and then in the v between 0 and 1 pi. We're taking half of the u domain for the v. So we'll take a look at what that means, or what that translates into Python in a moment. But the idea is that we're going to use that nested loop to iterate through the u and v in order to get these strips drawn out, so that we can actually make a parameterized surface, which we'll first draw as curves, and then we can translate it at the end into a surface. And then we can see here drawn out x equals sine of v plus cosine of u, y equals sine of v times sine of u times u, and then z equals cosine of v. Okay, so we'll try and remember those functions, and in order to help us, I'm going to just add in a comment here of what those equations are. So x equals sine of v plus cosine of u, y equals sine of v times sine of u times u, and then z equals cosine of v. Okay, so that's the equation for that particular parameterized surface. Now, if we go into our nested loop that we already have drawn here, we no longer need these added points. We're going to use this structure that we have above, where we're just using create point, so that we're not drawing all of these points in space. We're just constructing the values for them to be added to our polylines. So we need to translate the structure that we have above, iterating from 0 to 360, into these two nested loops. So if I change this value now back to 361 and 361, this is going to iterate in both the u and v from 0 to 360. So this would be the equivalent of iterating in radians from 0 to 2 pi. So if we remember our u and v domains here, our u domain was 0 to to pi. Our v domain, based on Joseph Choma's equation, is 0 to just 1 pi. So 1 pi is equivalent to 180 degrees. So in order to make that translation, we need to take a look at and determine a different domain than from 0 to 360. So if 0 to 360 equals 0 to 2 pi, then our u value is already acceptable. And in fact, if we wanted to add here, we could add the beginning value 0 to 361, iterating all the way up to 360 degrees. And then we just have a step of 1, so that will work for that domain that we have listed in his equation. Now, from 0 to pi, what we need instead is 0 to 181. So no longer is it 361, the full domain. We want to cut that domain in half to just range from 0 to pi. Otherwise, we'll double the amount of data included, which really just kind of fills out a different twist as it kind of continues iterating past where Joseph has chosen to clip it. He has sections on this idea of domain clipping and translation and transformation in trigonometric functions. It's a really incredible text, and I highly recommend reading it, buying it, in order to further understand these mathematical translations. But for now, this will just give a kind of sample taste of what this is all about. So next, if we want to do what we've done here in this singular loop, we want to construct an x, y, and z value, which can read in those u and v values into our trigonometric functions. Now, if we just placed those values up at the top and said x equals u comma v, we would totally omit this iteration through our v's. So we need to have that x, y, and z value set inside of our second loop. I'm going to comment out these print statements and then hit enter inside of that second loop. And this is where we're going to declare our x, y, and z values. Now we already have the functions here, but what we need to do, like we did up above, is we need to convert our degrees into radians using math.pi and then times our value divided by 180. So we're going to convert these equations by taking in the u and v values as radians, not degrees. So we'll say, we'll create a variable called urad and vrad. So these are going to be our u and v radian conversions. So urad equals our u value, and then we know we need to multiply this by pi. So we'll put this in parentheses, multiply this by math.pi, and then divide it by 180. Oh, not plus, sorry, multiply. And then we need to do the same thing for our v. And then we can just change that u to a v. So we've converted those degrees that we're incrementing or stepping through in both of our for loops into radians here, and we have a u and v radian input. Now we have these formulas for sine and cosine. In order to access those, again, as we did before, we need to type math.sine, open parentheses, and then place in our vrad, and I'm just following the function now, so vrad, and then plus math.cosine, and now we need our urad. Then our y equals math.sine, open parentheses, vrad, times math.sine, open parentheses, urad, and then all times urad. Lastly, we just have math.cosine of vrad. Now it's important to feed in radians as our trigonometric functions read in radians. So we need those angles to be measured in radians. So now that we've written out those equations, one way we can just test that this is working is by going into our rs.addPoint and replacing this with our x, y, and z values. So x, y, z. Now if I hit play, what we should see is our u and v's looping through our functions reading in, our x, y, and z values being set, and then points being added according to those rows drawn out in space. So if I hit play, and then looks like we need to zoom in a little bit, so we'll let it iterate through. And now we can zoom in on these points. We see all of these points drawn out in space, and we can click them inside of Rhino as they've just been created in our document. So I'm not using create point there, I'm using add point to actually add it to the document. So what we want to do, this is essentially a surface already, but we don't actually have the rows being drawn out here or any kind of operation to create that surface. Well, if we draw out the rows, then it's as simple as just using a function like loft to loft between all of those rows. So if I delete these points and then we go back into our Python function, instead of adding point like we've done above, we need to create, and then we need to append this to a points list in order to make polylines. One important note though is that we don't want our polylines to be made after all of the u and v values are iterated through, because this would just give us one continuous polyline looping through all of these rows. What's important for a surface to be constructed is that we have those rows separated in separate lists. So what we actually want is a points list, so points here inside of the u value, so that every time we iterate just through the v, we're appending to this points list, which we could also call row points, because these are our row points. So in order to add to that list, we need row points dot append. And now instead of add point, we just need to change this add to create. So now we have create point. We're adding the x, y, and z created point to our list, but we're not actually drawing a curve. Since we want to draw a curve every single time we step in the u, but then draw the continuous points all the way through, looping through all of the v values, what we need to do here is not draw it inside of this v function. That would draw a new line every single time we step in the v, which actually would give us an error because we wouldn't have enough points. We need to do this inside of our u loop after we've iterated through all those points and appended them to our row points. So what I'm going to say here is row underscore poly equals rs.add polyline. And if instead of a polyline, maybe we wanted to do an interpolated curve so that we have a bit of a smoother surface moving through, and we could just type add interp. Let's get that suggestion. So add interp, and then that's interp curve. And then we can just open up this parentheses, and interpolate curve is going to draw a curve exactly through the points, but smoothed between them. So it's similar to a polyline, and we went over this in the Rhino introduction, but it draws exactly through and kind of smooths between those points. And now what we need to feed in here is a list of points, as it says in our kind of help document at the bottom, so we can feed in our row points. So as it steps into the first iteration of the U, it's going to read all the way through this, and every single time it gets to that first iteration in the U, or then the second, third, fourth, and so on, it's going to read row points equals an empty list, clearing that list. So every single time it steps, it clears that list, and then we add all of the points back in, and then it clears again. What's important is that we're actually creating the curve between clearing the list, adding them back in. Once they've been added, we make the curve. We're not deleting the curve now, so we have this curve actually created, and we've added it to the document, and then we have that existing. So if I just hit play now, we should see curves being drawn out in space instead of points, which we are seeing. And they're curves drawn specifically at or based on those V rows. So if I click on one of these curves, we can see that each one is drawn as a separate curve. It's a bit hard to click on each individual curve. So each one of these is the incremented set of points in the V. So this is one full set of v points at one particular u location, or one particular u iteration. Now, what each of the curves represent as a set is all of the u iterations. So the u iterations are the different curves, and the points on each curve are the v's. So now what we need to do is translate this into a surface. If I select this and type loft, it may not do this, and you can see it's giving us an error that says some but not all of the curve endpoints touch. So this is a trick that in translating this into Python, we have to kind of fake a little bit. So what I'm going to do is just make that start at 1 instead of 0, so the points basically just don't touch. So if I hit play again, it's just going to remove that first V curve. So we can see it's removed that first V curve. And now if I select these and type loft, hit OK, seems like it's wanting us to maybe do this also in the U, so we can try that and then hit play. And this may work now. Some of these are a little tricky, but it has more to do with the actual loft function. So it's still drawing the same thing. We're just removing one point in the U and one curve from the V set. So loft, still having an issue there. I'll try one more time, and we'll just iterate through 1 to 360. So it's going to go to 359 and then 179. Now if I hit play, hopefully this is enough to change it so that we can actually perform that loft. Let's take a look here. There we go. So we now have our loft drawn out. And what it's able to do is read in all of those curves, and then between each curve, loft each one together. So essentially what it's doing is it's just automating the process of selecting these two curves, typing loft, hitting enter, selecting the next set, typing loft, hitting enter, and going all the way through these. So we can only do this because we've structured our curves in a way based on u and v values to make these parametrized surfaces. So if I go ahead and delete this, the last step here is to just add this into our Python function. So we can actually add the loft function inside of here by creating a list of polys or polylines, or we can say, I guess this is not row poly, this should be row curve. And then we can have a list of curves equal to an empty list. And then every time we make a curve, we want to add that. So curves.append row curve. So add that row curve to our list of curves. And then after we've made every single curve, we want to add a lofted surface, which takes an input set of objects or curves as inputs to this. So we'll take our entire list of curves and we'll make a lofted surface. Now when I hit play, it's going to draw out all of those curves, and then it's going to finish by constructing a surface, which we've done there. And we can flip this, turn off the ISOs, drag it out, and we now see that surface drawn out inside of Rhino. Then we still have the curves as well. I'm going to just go ahead and move this over. And one last thing, just to test a different equation here, just to give another kind of sample. What we're going to do is use or plug in an equation by Joseph for a twisted torus. So this is going to be our definition for a twisted torus, and actually this is a ribbed twisted torus, meaning that it actually has surface ridges or ribs as the torus is twisting around a center point. Inside of Joseph's book, he explains what each of these portions do and how it kind of rotates certain portions of the function or curves or surface. It's all linked together. But I'm not going to get into that in this particular video. If you are curious, buy his book and read it. And if you have any questions, feel free to reach out to me and I'm happy to answer them. The domain for this also is going to be, well, actually, you know what, we can start with a full domain and then I'll show you how we can actually edit the domain. So why don't we just go ahead and start with the full domain. So that's going to be here 0 to 361, and then our V, we can say 0 to, actually we'll do V 361, and then we'll do 360 for the U. So we're removing that last curve for the loft. Okay, now we're going to use the exact same structure, but just replace these X, Y, and Z functions. So I can just go ahead and copy those, or we can just paste them in. Now you can see here we have a little bit of different syntax for the U radians and V radians. Here we're calling them U rad and V rad. So we would have to reconcile that. So I can just, I'm going to delete these functions anyway in their entirety, and then we're going to go through and read the functions above. So X equals, we have 3 halves plus sine U rad plus V rad, all inside of the sine function. And then this has to be inside parentheses with 3 halves, so that we're performing that addition operation first. And then multiplied by cosine V rads plus cosine 2 times V rads over 10. Okay, and then we can see we have a pretty similar line for our Y value. So I'm going to just start by copying this down, and then we can make edits. So we have 3 halves plus math sine, so sine, U rads plus V rad, so that's going to be the exact same that we have. And then times, not cosine, but sine for that second equation of V rads plus sine here of 2 times V rads over 10. So that now cleans that up. And then lastly, we have our Z equal to sine of cosine of U rads plus V rads plus cosine of 6 times U rads divided by 6, and then just close those parentheses. Again, he talks about what that's actually doing and how we can get control over this in his book, but just trust me for now that this is the equation and that it works. Use those full names in here. So I'm going to just replace all the signs, math sine, and replace the cosine with math dot cosine. Just makes it a little bit messier, so I was hoping to clean that up a little bit for us so we didn't have to look at so much messiness. But okay, now we can go ahead and hit play. And we've also added rads here, but it's just singular rad. So vrad, 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 vrad. Okay, there we go. Now this should be good. Spelling mistakes are always an issue inside of Python, so we got to be careful. So our twisted torus was drawn at the origin, and then our surface was constructed. So I'm going to just go ahead and move this over here. And now what we're going to do is use Joseph Choma's slicing or cutting operations to basically use the domain, trim the values in order to only save some of these curves and then loft between them. So if we click here to see where those curves are drawn, we can see that our V loop is actually iterating through around the kind of XY plane almost. Maybe we can think of it like that, although it does transition. But I'll call this like an XY or horizontal plane. So the V points are drawn out across there, so these curves are relatively horizontal. Now, if we just wanted to remove, let's say, that set of curves, what we would need to figure out is what U values that equates to, and then just don't iterate through or don't loop through those values. So I'm thinking that's going to be maybe the last, let's say 45 degrees or so, just based on, or let's say 60 degrees. So that could be the last 60 degrees. So if we don't want to iterate through, or we don't want to include the last 60 degrees, what we do is change this from 0 to 300, meaning we're removing the last 60 curves, or 59. So if we do that, when I hit play, we should see that that last ridge is actually removed from our created surface. So it was, but we didn't go quite far enough. So we removed 60. It looks like we might need to remove a little bit more, possibly 90, possibly even a little bit more. Maybe we'll try 120 on the next one. So that is removing the last 60. If we go back to our code and then change this 300, so we want 360 minus 120, 240, and now if we hit play, we'll have that twisted torus drawn out all the way until the last 120 curves, and then it won't draw those last 120 curves. Now we could just stop there, or we could adjust the domain again, and we could even start from a different value as well. So we could start from 90 and go to 240, or yeah, let's say 90, and then hit play. And again, this is going to perform a clipping operation and only result in that strip that we have selected. It's a really beautiful, elegant form that's constructed. And I believe this clipped domain on the twisted torus of his is actually one of his Talon Biennale submissions. It's a really beautiful project. If you haven't seen it, I highly recommend trying to look it up and finding it. Joseph has also done some incredible work in fiberglass composites and thinking about ways of converting these not just through fabrication, but also through kind of structural principles and thinking about the structural properties of these ridges and shells. That's all for this introduction to Python exercise focusing on mathematical loops. In the next video, we're going to introduce aggregation through recursion and functions inside of Python.